Alright, on to part 2 of this video. Properties of polymers. Names properties of polymers. So addition polymers have specific properties. We can control these properties to create useful properties. They also have simple naming systems. So naming with polymers is actually very simple. The naming is the same way they have polyethylene is made from ethene units. Other polymers like polyphenolethene is made from phenolethene units. So the unit in itself, one unit of a polymer is just called the monomer, and many repeating units of the monomer would make the polymer. So and then you just call it poly, you call it poly and then the monomer name. So if it's, for example, if phenolethene is the monomer name, if I put the polymer of phenolethene, would be polyphenolethene, and that's it. Then this general format is this is the general format. If a molecule is polymerized, its name is just poly and then the name of the molecule. So when we're talking about the strength of these molecules, we're talking about the intramolecular forces, not the intermolecular forces, not intra, sorry. The intermolecular forces. Intramolecular is to do with the chemical properties, but we're talking about physical properties, we're talking about intermolecular forces. And intermolecular forces are just the forces that are between the molecules, in this case between the polymer chains. And these forces are weak van der Waals intermolecular forces. So we have weak van der Waals intermolecular forces. So as I said before, the intermolecular forces are strong as the molecules are huge. So there are lots of van der Waals intermolecular forces between them. So that's quite important, particularly the last part of the sentence, where it's like, so they're huge. Actually, intermolecular forces are strong as the, sorry, I should go from here. It's important to say because these bonds here are quite weak by themselves, but when you have many of them, that's what makes the bond, that's what actually makes it strong. It's not, because I see a lot of time they'll give you a question or they say, why is this molecule more stronger than another molecule? Why is there more energy required to break this molecule compared to this molecule? And it's because this is a longer molecule, but not just because it's a longer molecule. When you have the longer the molecule is, the more of these intermolecular forces will occur. And that's why you can't just say it's because one is larger. You won't get the marks for it. You have to say because it's larger, there'll be more occasions where you have these van der Waals intermolecular forces. More van der Waals intermolecular forces means more energy is required to break all the bonds between all the intermolecular forces between the molecules of the polymer, because that's quite a big mark that people miss out on. And there's two types of in addition polymer. There's two types of broad classes of addition polymers, and there's straight chain polymers, for example, polyethylene. Straight chain polymers are packed closely together and are strong and rigid. So, for example, this here would be an example of a straight chain molecule. You have, there's no side chains, so they form as many much more intermolecular van der Waals intermolecular forces between them, because there's no side chains that distort the shape of it. So it means that you can form between each one. It's going to form these intermolecular forces quite easily, and therefore, the more intermolecular forces that you have, the stronger it is. The more closely they pack to one another. They're not very bendy. They're not flexible at all. So and they're very rigid. However, if I was to pick, whereas when you have branch chain polymers pack less densely together and are more flexible. And it's kind of the same idea when you're talking about unsaturated fatty acids. If you ever heard, like, that's kind of like that is a good example of, like, for example, because when you're talking about saturated fatty acids, they're straight chain. Because of their straight chain, they easily stack up upon one another. But when you have unsaturated fatty acids, for example, the same principle applies, where it's not going to stack easily against each other, because For example, a double bond would not exactly the exact same principle, but the idea that because there's a kink to the structure, because there's a kink to the structure, it's not exactly the same idea, but the same kind of mindset when you thinking about there's a kink to the structure of the double bond, and that prevents certain van der Waals intermolecular forces from happening, and therefore they pack less tightly together, and they pack less tightly together, less van der Waals intermolecular forces. It's weaker, liquid at room temperature. Now, you're not talking about double bonds here, but I'll give you an example to show what I mean here. You won't have a double bond necessarily, but it's more to do with the fact that you have side chains. You know, that if I was to have in the polymer chain, and I had this structure here, for example. Let's keep this as CH2. Do you know what? I'll probably. You know what? Yeah, no. Leave it CH2 here, CH3, or if we're talking about polymers, I could change that to a CH2. And then carry on. Now, if I was to do the same thing here, obviously it's not going to be exactly straight chain like this, but this is just to show you an example of my point. This is forming easy van der Waals intermolecular force. There's easy, and even to an extent here, technically easy, but here, this massive methyl group is preventing me from forming a van der Waals intermolecular force. You can, they will eventually form, but when they have, overall, it's much harder for them to form, and there'll be a molecule above this one as well, and it's much harder for them because this is blocking it. And that when that occurs, that means that less van der Waals intermolecular forces happen, and this one is not going to be a problem. But when you have multiple of these, there's a massive problem, because it's going to be a massive problem. There's a massive, there's not going to be a lot of those van der Waals intermolecular forces. I shouldn't say a problem, because sometimes you want this to happen. Maybe you want, this isn't actually a bad thing to happen if you want to have flexible plastics, for example, shopping bags or IV drip bags. You want them to be flexible in order for them to fit the contents of what you want them to be, and maybe you don't want your plastics to be rigid, so it's not bad to have these type of molecules, but to understand what's going on here is that there's less van der Waals intermolecular forces, and therefore that's what causes the strength of the polymers to be weaker and more flexible. To bring back a point that I had to have before, when I had the previous structure, great. One thing I want to make sure that I have to stress that this is a weak van der Waals intermolecular force. On the ones that are actually not very strong, but when you have many of them, that's what makes them strong. That's why it's the same reason behind why it's easy to tear one piece of paper. When you have it's easy to tear a single sheet of paper, but it's very difficult to tear a stack of A4. They're all equally paper, but when you have multiple of those bonds together, it makes it much harder to break. Reactivity of addition polymers. So addition polymers are often unreactive, and due to the fact that if the monomers were reactive, you'd get many side reactions during polymerization. Addition polymers aren't very reactive, as the carbon chain is saturated and the side chains are usually non-polar. So these are for addition polymers, these are carbon-carbon covalent bonds. They don't react. They're not polar at all. Not very unpolar. It's very non-polar, should you say? I guess there's technically some polarity because the bond is there, but they don't break. A lot of energy is required to break them down. In fact, one of the questions that you might get in your exam is why you probably have a condensation. You choose a condensation polymer over an addition polymer, because it's better to use a condensation polymer because they can be broken down by hydrolysis, making them more biodegradable. you know, you can't. A lot of energy is required to break down carbon-carbon covalent bonds, and they're not regarded as being biodegradable. So that's one thing that, you know, it shows that they're very unreactive. And so this is just here to show you all the polymer classes. So so polymer classes, polymers can be distinct into straight chain polymers, which are strong and rigid, or branch chain polymers, which are flexible. You can modify polymer properties. So the properties of polymers can be modified using plasticizers. And plasticizers, what they are is that we can make straight chain polymers more flexible using plasticizers. And plasticizers are molecules that stick between the chains and keep the polymers further apart from each other, and they weaken the van der Waals intermolecular forces, allowing the chains to slide easier, meaning monomers are more flexible. If you didn't get what I meant, basically I'll just say I'll show you what it means. What it means is that what plasticizers do, if you have a very rigid straight chain polymer that it's you want it to be more flexible, what you do is you have plasticizers, and these plasticizers move in between. They just move in between. You have multiple of them, not too many of them, but you have enough of them. They'll move in between these van der Waals intermolecular forces between the polymer chain, and they prevent van der Waals intermolecular forces from actually occurring between the two polymers. And therefore, if there's less van der Waals intermolecular forces, the structure of the polymer is much weaker. More energy is required to break the bonds. So less energy is required to break all the bonds, but ideally, it's more flexible. That's the most important thing, and that's why plasticizers are much used in the industry. However, plasticizers have downsides to them. You know, although they can be used in industry for making, you know, for example, plastic bags, or there are uses of these plasticizers for example, plastic bags they need to be more flexible in order to fit all the content you need inside them. However, plasticizers, when they wash away or when they get thrown away, they can cause, you know, plastic in the ocean, because plasticizers don't really break down. They don't really break down really in water. They don't dissolve or anything like that. So they can just accumulate in seawater, and that can lead to other complications, mostly in the ocean. So polychloroethane, also known as PVC, is formerly known as polyvinyl chloride. PVC is used for rigid plasticizers, i.e. drainage pipes, as a strong dipole forces due to the presence of a chloride atom. When plasticizers are added, flexible PVC materials can be made, which can be used in flooring tiles. So that's just an example of. I don't think you actually you don't really need to specifically know any example of plasticizers apart from phthalates, which I do believe. I think you do need to know PVC and phthalates. That's what I'm wrong. You do need to know PVC and another example called phthalates. So phthalates this is not obviously what it looks like, but it's just me kind of doing a scribble. But you do need to know of them, but not of their structure. You just need to mostly know that, for example, PVC or phthalates, and you just need to know what plasticizers actually do and how they could be useful. Because you're never going to get a question that just says what they do. It's very unlikely you're going to get that in a chemistry exam. It's more, how can it be applied? And I guess if just to show your understanding, you know,